Let's look at a few more applications of the molecular orbital theory that we introduced in the last video. When you're applying molecular orbital theory, the first thing that you need to have is a molecular orbital diagram. And we did this one last time. We saw that if you've got two s orbitals and they're interfering with each other, they can interfere constructively to make a bonding orbital, or destructively to make an anti-bonding orbital. You should know this energy level diagram. Here's the low energy state, the ground state, and here is a higher energy state. And we can fill these things in with electrons. We did that last time. Each of these orbitals can hold two electrons, one spin up, one spin down, just like atomic orbitals did in our orbital diagrams for atoms. But this is an orbital diagram for a molecule. The other thing that we talked about last time is figuring out bond order, whether you have a single bond, double bond, triple bond. And we said that's the number of bonding pairs. Each bonding pair makes a bond. Each anti-bonding pair breaks a bond. So this is what we did in the last video that you should carry forward. Let's put a box around this. This is what you should know to start off problems with molecular orbital theory. Now, let's use this to describe a couple of different molecules. How about this molecule, which they think was one of the first molecules to form in the universe after the Big Bang? It's an ion. Okay, well, it's got how many electrons? Helium has got 2 electrons, and hydrogen has 1. But it's got a plus charge on it. So we would have 3 electrons just from helium and hydrogen, but then there's a plus 1 charge. That's going to take away an electron because there's a missing electron there. So I have 2 electrons. So let's do a molecular orbital diagram for HEH+. Alright, if I've got 2 electrons, I'm going to fill them in from the bottom up. One spin up, one spin down, that one's done, and I'm out of electrons. So this is the molecular orbital diagram for this. What's the bond order? Well, there's a bonding pair, so that makes a bond. And there's no anti-bonding pair to break it. So my bond order is 1. So there's a single bond between, according to molecular orbital theory, there's a single bond between the helium and the H+. And this is exactly what you got when you did the Lewis structure for this. Go back and look at this on one of your worksheets. You had this. Your Lewis structure looked like this. Alright, so molecular orbital theory and the Lewis theory very often agree. Now, let's do one more. Let's do a negative ion this time. Let's suppose I have H2, but I've given it a negative charge, and I want to write an orbital diagram for this and see what I can tell. I can learn about the molecule from that. Well, here is my molecular orbital diagram. And how many electrons do I have? Well, I have 1 for each hydrogen. There's 2 hydrogens in there. And then I have an extra 1 for the -1 charge. So I've got 3 electrons. Alright, so let's fill them in. 1, 2, that one's filled, I have to go up here. 3. All right, what's the bond order? I have a bonding pair, so that's a bond, and I have half of an anti-bonding pair. So I'm going to be left with half a bond. And this is something that you can't easily show with Lewis theory. In fact, Lewis theory won't give you a good structure for this molecule. So there's a half a bond between the two hydrogens here. Now, if you've got a lower bond order, that means you have a weaker bond. It also means you have a longer bond. So I would expect, we saw that you had a bond order of 1 in H2. I would expect that putting that extra electron makes the bond only half a bond. It's going to be weaker and it's going to be longer than the bond length in an H2 molecule. And I can tell all of that from this simple little diagram. There's another thing that I can tell. This has an unpaired electron. Now remember that electrons, because of their spins, are like little bar magnets. So this has got a bar magnet that isn't canceled out by another one. These two have little magnetic fields around them, but they cancel each other out. One's going up and one's going down. This one doesn't have anything to cancel it out. And that means that this molecule is going to have a net magnetic moment, we say. It's going to be paramagnetic. If you have any unpaired electrons, your molecule is said to be paramagnetic. And what does this mean? It means that if you were to have a magnet, this stuff would be attracted to it. And if you were to weigh some H2 minus in a magnetic field, its weight would be different than it would be out of a magnetic field, because it would be attracted to the magnet. So this would be a paramagnetic molecule. So you can tell whether a molecule is paramagnetic or not by how many unpaired electrons it's got. If it doesn't have any, it's not paramagnetic. If you have no unpaired electrons, or you could say unpaired spins, you could say either unpaired electrons or unpaired spins. The opposite of paramagnetic is diamagnetic. So you could say it's diamagnetic if it had no unpaired spins. The HEH plus is diamagnetic. Alright, so we can tell all of that from just the molecular orbital diagram. In the next video, we're going to look at some more complicated molecular orbital diagrams. Now, I expect you to know this one. It's pretty simple, but the ones we'll do in the next video will always be given to you. You must do a molecular orbital calculation on a computer in order to get these energy levels and see how far apart they are. And it's a very complicated calculation. So it's beyond the scope of the course for you to get anything more complicated than that. I will have to give you a molecular orbital diagram and then ask you to interpret it for me. And that's what we'll do in the next video.